Hi, you are welcome to today's session. In today's session, we'll be looking at redox reaction. Redox reaction. And our learning outcome for this session will be that at the end of this session, you should be able to define oxidation and reduction, identify oxidizing and reducing agents, especially in redox equation. You have to recall on your knowledge of calculation of oxidation number or oxidation state. And likewise, you have to solve exam style questions on redox reaction. All right, so let's take a look at this. So a man came from another planet, came to planet Earth and saw this. And he wants you to explain what you have seen in the picture to him. You have 3 nails. So this first one, clean. So the second one, tarnished. Third one, wet tarnished. So what would be your explanation? Okay, I know basically you'll be saying this is rusting. The nail is made of iron, so an iron rust. So if you can do this, then you are not far away from redox reaction, because rusting is a typical example of redox reaction. So you're having iron, changing from one state to another state, and with a color to indicate that something has taken place. So that is basically an idea about redox reaction. So what is redox? Redox reactions involve both reduction and oxidation. So a redox reaction is different from molecular equation. In a redox reaction, there must be reduction and oxidation. And what is oxidation? You can be asked to define oxidation in terms of oxygen. So we can say that oxidation is the addition of oxygen to a substance or the loss of electrons from a substance. If it has to define in terms of electron. Likewise, reduction is the removal of oxygen from a substance or the gain of electrons to the substance or addition of electron to the substance. Basically, this acronym will help us oil rig. Oil rig. So what does this mean? This is basically saying that the O is basically saying that oxidation is loss, okay? Why this one is, the R is saying that reduction is gain. So that can be something to guide you all through this class. Oil rig. Oxidation is loss, reduction is gain. So any reaction that involves loss of electron and gain of electron is a redox reaction. So we have some equations that there is no gain or loss of electron. A such equation is simply a molecular equation, simply molecular. H2SO4 plus sodium hydroxide, gives you this plus this. You can add 2 here. When you have this, there is no loss of electron. Okay, there is no loss of electron. Basically, the electrons are the same. If I calculate the number of electrons here, and that's how you call this on surface 6, is still surface 6. So the electron, the oscillation state remains the same. When you have such reaction, such equation, they are molecular. They are not redox reaction. So for a reaction to be a redox reaction, there must be loss of electron and there must be gain of electron. Both must happen. And as I say, redox reactions involve both reduction and oxidation. But there are other ways in which we can define oxidation and reduction. There are other ways to look at them. So let's quickly consider these other ways. We can look at oxidation as addition of oxygen to a substance. So for instance, here you have calcium turning to calcium oxide. So in this case, calcium is oxidized. Oxygen has been added to calcium. So we say calcium is oxidized. We can see reduction as a removal of oxygen. When you remove oxygen from a substance, that is basically a reduction. You remove oxygen from a substance. So here we can see copper oxide contains oxygen. This copper oxide has turned to copper. The oxygen has been removed. So we say copper oxide is reduced. Why? Oxygen is removed. Another way to look at oxidation is that removal of hydrogen from a substance. Removal of hydrogen from a substance. So here we have an equation. Hydrogen sulfide is now has turned to sulfur. Hydrogen sulfide has turned to sulfur. So if I move from here to here, I will say that hydrogen sulfide is oxidized. Why? There is removal of hydrogen. So the hydrogen that is with sulfur before in hydrogen sulfide has been removed. So I now have sulfur alone. So this is simple oxidation. So anytime there's a removal of hydrogen from a substance, it's oxidation. All right. In reduction, just like opposite, addition of hydrogen to a substance. Most often, just know one part of it, and you know that is the opposite of it. So addition of hydrogen to a substance. So what am I doing here? Hydrogen gas plus chlorine gas, you have hydrogen chloride gas. So here, chlorine gas is reduced. How? This is chlorine. 2 atoms of chlorine in a chlorine molecule. Now I'm only having 1 atom here. Only 1 atom. So that means that hydrogen has been added to chlorine. Hydrogen. I only have chlorine here before, but hydrogen now has been added to chlorine. So basically, this is reduction, addition of hydrogen to a substance. There are other ways to look at it again. We can also see oxidation as addition of electronegative elements. Because when we say electronegative element, talking of, chlorine, bromine, iodine, and so like even oxygen as well. Okay. So when you have addition of electronegative element, this is copper, it has turned to copper chloride. Chlorine has been added to copper. So that is copper is oxidized. Now, this is not basically, if the number of chlorine atom increases, we also see that as addition of electronegative element. For instance, if I have Cl2 here before, and it undergo a reaction that turned it to Cl3, maybe something else was added, and you have SCl3. Here you have XCl2. We also see this as oxidation, addition of electronegative element. Likewise, if peradventure a more electronegative element is displacing a less electronegative element, it is still oxidation. All right. In reduction, we'll see it as removal or reduction of electronegative element. So if there is removal of electronegative element or there is a reduction, then I will say that is reduction. Take for instance, look at this. 2 chlorine atoms, only 1 chlorine atom. So chlorine is reduced. Chlorine is reduced. Likewise, we can also see oxidation as loss of electrons from a substance. Loss of electron from a substance. So if I have this is magnesium, it has lost 2 electrons. So You know, basically, if I have magnesium, I can look at magnesium is this 282, okay? And of course, this one is just 28. So it has lost these 2 electrons. So if it loses electron, then definitely it becomes oxidized. So the 2 electron that is lost is here. All right. So it has lost 2 electrons. That is oxidation. In terms of reduction, we can say that when there is addition of electron or gain of electron, remember oil rig, oxidation is loss, reduction is gain. So instead I'm saying addition or I'm saying gain. So in between here, I'm saying oil rig. All right. So if I take a look at this, I know that chlorine here is 288. So because it has gained 1, while chlorine here is 287. So this chlorine has gained 1 electron to become 8. That addition of electron is basically reduction. Another way to see oxidation is that oxidation is increase in oxidation number. So I can just basically use the charge. Okay, 2 plus has turned to 3 plus. If there's an increase in oxidation number of state, then that is oxidation. For this, if there is a decrease, plus 3, it has turned to plus 2. I will say that is a reduction. That is a reduction. Now let's look at oxidizing and reducing agent. A substance that brings about oxidation in another substance is called oxidizing agent. But at the end of the reaction, this oxidizing agent must become reduced. The oxidizing agent must become reduced. We have examples: oxygen, oxone, chlorine, bromine, nitric acid, conc H2SO4, and others. So these are examples of oxidizing agent. In a reaction, this oxidizing agent will cause other substances to undergo oxidation, but they themselves will become reduced. You know, practically, we can test for oxidizing agent, you know, based on some reactions. Take, for instance, we can test oxidizing agent, you know, maybe you add with iron chloride, and you expect to have a change from green to brown. From green to brown, because basically what you're having there is you're having from iron 2 plus to iron 3 plus. So we can use this one to test for an oxidizing agent. All right. We can also use potassium iodide, where you expect that this basic reaction here, this is what is happening there. Okay. Moving to, so you expect that this one will move from colorless. There'll be a change from colorless to brown, from colorless to brown. So when you have this, you are reacting an oxidizing agent with iron 2 chloride. Okay, and you have a change from green to brown. If you react an oxidizing agent with potassium iodide, okay, from colorless to brown. But what is actually happening there is that iron 2 plus is turned to iron 3 plus. Iodide is turning to iodine. So that is basically one. Then also, you can also use starch iodide paper. In that case, you expect a change from white to blue or dark blue. So when you have that, that is also a test for an oxidizing agent. All right. A substance that brings about reduction in another substance is called reducing agent. At the end of reaction, this substance become oxidized. So it will cause another substance to undergo reduction, but it itself will become oxidized. And that is why we say redox reaction. Both the oxidizing and reducing agent must interact together simultaneously together. All right. Examples include hydrogen, sulfur dioxide, hydrogen sulfide, carbon monoxide, carbon, and metals. These are reducing agents. And how do we test for them? We could test for this basically by using potassium permanganate. And the reaction you are having there basically is having from here turning to 2+. And we know that the color of this one is purple, so it will change to colorless. Or you say it will decolorize it, colorless. Yes. So any substance, if the substance, not all substance though, but if you are testing for reducing or oxidizing agent, okay, we have other substances that can be oxidized. All right. But if you are testing for a reducing agent and you react with it, potassium permanganate solution, the color will be from purple to colorless. That is an indication that that substance is a reducing agent. Another one we can do is using potassium dichromate. That is K2CR2O7. Okay. The basic reaction that you have here is this. That's the basic reaction. So these two will change from orange. The color is orange initially. It will change to green. So when you do this practically, that is a test for reducing agent. Changing of potassium dichromate from orange to green and decolorizing potassium permanganate. That is a test for reducing agent. So, but in exam situations, especially where you just need to identify them on paper, you're not doing any practical, then the knowledge of half equations will help us to identify reducing and oxidizing agents. Take, for instance, in this equation, we are to identify the oxidizing and reducing agent. The first thing you need to do is to split it to half equation. When we say half equation is oxidation and reduction. That is half equation. So let's try to split this. If I move from zinc to zinc oxide, and I move from copper oxide to copper. So the question I'll be asking myself is, which of these is oxidation, which one is reduction? Let's start from zinc. Okay, zinc is oxidation. Why? Addition of oxygen. So oxidation. The reason, addition of oxygen. So oxygen is added. All right. From copper oxide to copper, this reduction. Okay. The reason, removal of oxygen. So that is my reason. So after you have established this, maybe I just want to confirm, or because if I see another question where there is no oxygen at all, then I still want to know if there is oxidation or there is reduction. So I can still look at other definitions. Take, for instance, what is the oxidation state of zinc here? This is 0, is free state. All right. Here, oxidation state of copper is +2. When I'm solving other question, maybe I'll split this properly. Zinc here is +2, copper here is 0. So I will know that zinc has moved from 0 to +2. That is increase in oxidation number. Increase in oxidation number. So definitely, if there is an increase in oxidation number, then it is still oxidation. Copper has moved from +2 to 0, so that is decrease. So that is reduction. So therefore, these two definitions has been established. No, any species that undergo oxidation is a reducing agent, because at the end of the reaction, it gets oxidized and it causes another substance to, are you getting now? So any species that undergo reduction is an oxidizing agent, and that is why it itself gets reduced at the end of the reaction. So if I can split into half equation, the one that undergo oxidation is a reducing agent, while the one that undergo reduction is the oxidizing agent. Or basically, you can just look at it from here, is the one that contains oxygen, so it's the oxidizing agent. But since it's not in all cases, and that's why I try to do the calculation for oxidation number, it is not in all cases you must have oxygen, since there are different other definitions of oxidation and reduction. So if you use the half equation method, you'll be able to identify oxidizing and reducing agent easily. So let's solve some questions there. Let's look at question 1. Say, in the reaction above, which the oxidizing agent is what? So let's try and look at the reaction by solving using half equation. So I move zinc here. I move copper to copper. So I will ask myself, which one is undergoing oxidation? Which one is undergoing reduction? So I know that oxygen has been added to zinc, so it's oxidation. Oxygen has been removed from copper. This is reduction. So any substance that undergo oxidation is a reducing agent. And we have also established that metals are reducing agents. We have established that metals are reducing agents. So any substance that undergo reduction is an oxidizing agent. Okay, the presence of oxygen there also make it an oxidizing. So here, our oxidizing agent is this. All right. Let's look at question 2. In the reaction above, the oxidation number of the reducing agent changes from. So we must first identify what is the reducing agent, because they are asking us the oxidation number of the reducing agent. So we have already established this in the question we first solved, that this one undergo oxidation and therefore is a reducing agent. It's also a metal. So now all we need to do is to find the oxidation number of zinc. Since zinc is in a free state, every element in free state that does not have any charge has a total oxidation of 0. If I have something like this, SO2, since there is no charge on it, then definitely is 0. Once there is no charge on it, it's 0. Okay? So we can say the oxidation state of zinc here is 0. Now, we must find the oxidation state of zinc here. Likewise, zinc sulfate, we have a total oxidation state of 0 since there is no charge on it. Now, what do I mean when I say charge? If I have SO4 2-, there is a charge on the ion, then the total oxidation state is going to be -2, corresponding to the number of charge on it. If I have OH-, the oxidation state is going to be -1, corresponding to the charge. So if there is no charge at all, that means it's in a free state. So definitely is 0. That's the total oxidation. So I must need to find for zinc here. If I'm to do this, I'm going to take SO4 as a radical. All right. When I say radical, The oxidation state of sulfate here, sulfate 6, is -2. How do we come about that? Sulfur has a valency of 6. Oxygen has an oxidation state of -2. But we have 4 atoms of oxygen here. So that is basically saying 6 minus 8. So that is -2. So if that should be the case, I can now say that zinc -2 equals to 0. So zinc equals to 0 plus 2. So zinc equals to +2. So we can see basically here that the oxidation state of zinc here is +2. So the oxidation state of the reducing agent has moved from 0 to +2. I don't need to bother myself with that of copper because they ask me for the reducing agent. All right. Let's look at question 3. What is the oxidation state of chromium in K2CR207? All right. This is potassium heptazodichromate. So they're saying dichromate what? If you know the dichromate already, you are fine. So how do we solve this? This doesn't have any charge. It's in a combined state, but it doesn't have any charge. So the oxidation will be 0. But most often you may want to ask, what if we're not giving for potassium, we're not giving for oxygen? Do we just know the number found? We can use the idea that was treated in our video when we were talking about properties of matter. So if an element belongs to group 1, an element belongs to group 1, group 2, group 3, group 4, 5, group 6, group 7. Let's leave this one out. If an element belongs to group 1, then its oxidation state is +1. If it's in group 2, +2. In group 3, +3. In group 5, -3. In group 6, -2. In group 7, -1. So basically, all I need to know is what is the group. So for potassium, I may want to know what is the atomic number of potassium. The atomic number of potassium is 19. So potassium is going to be 2, 8, 8, 1. And we know that the last number, of course, the electron in the valence shell or the electron in the outermost shell corresponds to the group. So definitely potassium is going to be +1. But we have 2 atoms of potassium. So this makes +2Cr, then plus. Now, we can also do for oxygen. Oxygen is 8. So I'm having 2, 6. It belongs to group 6. So the valence is -2. So I'm now going to have 7. Since I'm having 7 atoms into -2 equals 0. So this is 2 plus 2Cr minus 14 equals 0. Then I can now say 2Cr equals 14. Of course, this crosses to the other side because positive, -2. So I'm having 2Cr to be equals to 12, and Cr will be 12 divided by 2 because we are dividing by the coefficient. So I'm having a +6. So I can name this easily if I want to name now. This is simply potassium. So if you know the name, there may not be need to do a lot of calculation. Heptaoxo dichromate 6. So that's 6 that you see when you are naming compounds. also correspond to the oxidation state. So in some exams, there is no need to calculate. They say, find the oxidation state of sulfur here. If I know the name of this substance to be tetrazosulfate 6, then it's going to be the same. The oxidation state of sulfur will be 6. If you do the calculation, you still get the right answer. If I have H2SO4, equals to 0. Hydrogen is placed under group 1, so oxidation of 1. So plus X minus 8, you didn't know, that is 2 into 4 plus 2 into minus 4 equals 0. All right. So 2 plus X minus 8 equals 0. And S equals to 8 minus 2, and that will equals to 6. So what I'm trying to establish here is that if you know the name already, you can save time without calculation. It's only in cases where you don't know the name. But if you know the name, you know that this one is tetraoxosulfate 6. So if it is sulfate 6, that is the oxidation state. So that may not be need to calculate. But if I want to know sulfate what, then I may need to calculate using this method. All right. The reducing agent in the reaction above is what? So this is just to further extend our knowledge on half equations. So we still solve in the same way. We have done the first one for oxidizing agent. Let's do for reducing agent. So I will still pick this one here. I will split into half equation, okay, and take this one here. So if I have this, which one is oxidation, which one is reduction? So I can see that oxygen has been removed from water. So this one is reduction. Oxygen has been added to carbon. This is oxidation. So in that case, the substance that gets reduced is our oxidizing agent. The compound that gets oxidized is our reducing agent. So the reducing agent here is simply carbon. Which of the following reaction is an oxidation process? Which of the following reaction is an oxidation process? So for us to do this, we must pick this equation one after the other. They are all half equations. They are not full equations, they are half equations. So we must try and find out. There is no oxygen here. So I cannot say, oh, they have been added to oxygen. Oh, removal of hydrogen. I can't say that. So we have to look at another definition and remember that we can also define oxidation as increase in oxidation number. And of course, reduction will be decrease in oxidation number. So let's take a look at this. The oxidation number, since is charged, is an ion, is +2. We pick a charge that is corresponding. So that is +2. Since this one is a free state, is 0. So definitely from +2 to 0, that is a decrease. So this is reduction. Reduction. Let's take a look at this. The oxidation state of oxygen here is -2, corresponding to this charge. The oxidation state of oxygen here is a free state, is 0. All right. -1 and -2, which one is greater? Oh, don't say -2, because -1 is actually greater than -2. So if that should be the case, then 0 is greater than -2. So there is an increase. When someone adds 0, is better than losing something. I don't have, is rather than I'm owing, I've lost something. Okay, so this is an oxidation process because there is increase in oxidation number. All right. Let's move on and look at this. What is the oxidation state of chloride ion here? We can solve that easily since this one is combined. So if I have OCl minus equals -1. So since I'm looking for that of chlorine, oxygen has been established to be -2. So -2 plus chlorine will be equals to -1, because chlorine will be equals to -1 plus 2. That is basically saying 2 minus 1. So that is +1. So oxidation state of chlorine here, chloride here is +1. Oxidation state of chloride here is -1. So that is a reduction. Reduction. Okay, from +1 to -1. That's reduced. Here, the oxidation state of chlorine is 0, or chloride is 0, and here is -1. Since there is no charge on that, so if I have 0 and -1, of course, this is also reduction. From 0 to -1 is a reduction. So we are left with B, which is the one that has undergo oxidation. Question 6 is that if acidified potassium dichromate 6 act as oxidizing agent, color changes from, so this is just a white hat information. It's just a fact. There's nothing to think about. It's just fact. So we know that it changes from orange to green. That's been given to you from the beginning. That color is not yellow. Okay, it's actually, so we can cancel out yellow easily. So it changed from orange to green. Now, in the equation above, they are saying Y is what? Y is what? Now, for us to solve this question, we must have an idea of how to balance redox equation. And I'm going to do that very quickly. How do we balance redox equation? All right. To balance redox equation, we are going to back to that question. We can use the method which I call S-back. What is S-back? Can say split. Okay, so that split means split into half equation. Split into half equation. You must learn to split into half equation. B simply means to balance. What are you balancing? Balance atoms and then balance charge. I think this should get you started. This is not all, but it should get you started when you are solving such equation. So basically the question you have MnO4- plus iron 2 plus to give you Mn2 plus iron 3 plus. So for me to balance this equation, the first thing is I will split it into half equation. So I want to split this into half equation. So by splitting, I mean I'm bringing out the one that is oxidation and the one that is reduction. So I'm picking this one out first, turns to Mn2 plus. Remember our split equation where you are splitting the one that moves here to here, and you are splitting the one that moves here to here. That's what you are splitting. So if I split this, I will know that this is removal of oxygen. So this is reduction. Reduction. And of course, for this, iron 2 plus has moved to iron 3 plus. So this is basically oxidation. Why? It is oxidation because oxidation number has increased from 2 plus to 3 plus. From 2 plus to 3 plus. So after I might have done that, I've splitted and now I want to balance. I must first balance atoms. Now in balancing of redox equation, we can do it in two medium, acidic medium and alkaline medium. So those are the two medium. But in this session, we'll be focusing on acidic medium. How do I balance in acidic medium? So if I want to balance in acidic medium, because this is going to say acidified, we look at the question, there's acidified, so that's how you will know. If I have MnO4 minus turns to Mn2 plus, and I want to balance the atoms, how do I balance the atoms? In acidic medium, let's say acidic, if there is one deficiency of oxygen, I must balance with one molecule of water. One oxygen will be balanced with one molecule of water. So here, how many atoms of oxygen do I have? 4. How many do I have here? Nothing. So that means 4 oxygen is missing. So I must balance it with 4H2O. 4H2O. What does this mean? If I have SO2 and SO3, here I have 2 atoms of oxygen here, then 3. If I have this kind of equation, I'm just going to balance with only H2O. Since only one oxygen is deficient, only one. So because of that, I will only balance with only one molecule of water. But here I have 4 deficient. So this manganese doesn't have any, this manganate ion doesn't have any oxygen at all. So 4 is missing. I must balance with 4 molecules of water. If it is 2 that is missing, 2 molecules of water. And since I'm balancing atoms, I know that here now I have one manganese atom, 4 oxygen atom, 4 oxygen atom. But I don't have hydrogen atom. So I must balance the hydrogen atom by counting. This one I'm basically counting. 4 times 2. So that is 8 hydrogen. And since acidic, we are going to balance with hydrogen ion. So here, the number of atoms is balanced. In the opposite side, ion 2 plus has gone to ion 3 plus. So here, 1 atom of ion, 1 atom of ion is balanced. So there's no need for me to do anything again. No deficiency at all. So I'll move to the next step. I've balanced atoms. Don't forget, we splitted. We talk about balance. We've balanced atoms. Now we need to balance charge. How do I balance charge? Look at the number of charge here. The number of charge here is -1. Here is +8. So 8 times 1, 8 plus 8. The total charge is +7. That is the charge. Here, the charge here is +2, because the charge on top, and 0. So the total charge is +2. The charge is not balanced. So what must I do? What must I do to have the charge balanced? What must I do to have the charge balanced? So basically, that means I must, and since we have said that reduction is gain, so that means this one must gain 5 electrons. So basically, I can now add +5 electrons, since it must gain. So that I can now say +5 electrons. Since the electron is negatively charged, that will be 7 minus 5. Okay, and this will also give me +2. So the charges are now balanced. The charges are balanced. And if that wants to get a bit confusing, let me do this. All right, so if I have 5 electrons, this is negative, I can just say minus 5 straight. 7 minus 5. And then I can just say I have plus 2. So from both sides, I now have plus 2 and plus 2. The charge is balanced. Why for here, I have 2 and I have 3. I know that oxidation is lost, so this one must lose an electron. So basically, I will now say this plus electron. So if it loses 1 electron, so that will be, so that it cannot be plus 3, minus 1, plus 3, minus 1. So that will now be plus 2. So the charge are now balanced. So like I said, S back is not the only way to, is not the all method to solve it, but it will get you started. Now you have balanced atoms, you have balanced charges, but what remains? In redox reaction, the number of electron gain must be equal to number of electron loss. So it's like you are solving simultaneous equation. Number of electron loss must be equal to number of electron gain. It's happening together. So if 1 electron is lost, this cannot gain 5 electrons. So that means to make that equal, I will multiply this place by 1 and multiply this one by 5, such that I can now have 5 Fe 2 plus to give us 5 Fe 3 plus 5 electron. So here we have been able to establish that number of electron loss is the same as number of electron gain. Since we multiply this 1 by 1, the equation remains. So basically, I can now cancel the electron here and cancel the electron here. That is all. If I've done that, then I can now combine the equation. I can combine. You see, if I combine this, can you see now? This is what we have. Okay. Look at this equation and compare, even before we cancel. Compare. So I'm compare. If I'm to combine this, look at this. Okay. We have, let's combine this together. You know, we split it in the beginning. Now let's bring it back. MnO4, 8H plus. Are you getting now? MnO4. So all this, let's write it out. You know, and this one, because they are both on the left hand side, we are going to combine them together. So I'm combining them here. So that is MnO4 minus plus 8H plus 5Fe 2 plus. All right. So let's go back. The one on the right hand side now. These are the one on the right hand side. This and this. Now we have cancelled out that electron. So let's put it together. So this is Mn2 plus 5 Fe 2 plus 4H2. So because we could balance that. So when you have such this kind of question, you must know how to balance. So I can now identify what Y is easily. This is the only thing that is not there. MnO4 here, MnO4. 5Fe, 5Fe. Mn2 plus, Mn2 plus. 5Fe2 plus, 5Fe2 plus. 4H2O, 4H2O. So definitely this is representing Y. So it corresponds. So C will be our answer here. All right. So those are the way we could identify redox reaction. We could identify a missing number in a redox equation. So thank you for coming to chemistry session for today. In the next session, we'll be looking at electrolysis 1. Thank you.